Hi everyone. This is a video on sample size calculations for the mean, for the population mean. So here we're going to start off with a problem. 60 water samples are randomly selected from the Gallatin River, and the mean dissolved oxygen levels, a measure of water quality, in these samples is 9.5 parts per million. Estimate with 99% confidence the mean dissolved oxygen level in all samples, essentially in all water, from the Gallatin. Assume that the standard deviation of dissolved oxygen levels in all samples is 1.2 parts per million. So the first step in this process is determining if you can actually do the problem. So the validity conditions for a confidence interval, you have to have a random sample, and we have a randomly selected sample of water, so that checks out. So random sample of water samples. Either the population is normal or n, the sample size, is bigger than 30. We selected 60 samples, which is bigger than 30, so we have that part. So n, in this case, equals 60, which is bigger than 30. Lastly, sigma is known, and sigma, which I'm going to ask you to write in words, is the standard deviation of the population. So I would say for that the standard deviation of the population, which is the amount of dissolved oxygen in all samples, that makes it the population, is known. All right, so again, write out the sigma. Don't just say standard deviation is known. Don't just say standard deviation of the population, but what is the population? In this case, it's the amount of dissolved oxygen, O2, in all samples. Okay, so each of those conditions, check, 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 check out, which means that our process, our confidence interval, is valid. Means you can actually complete the problem. All right, so we know the confidence interval formula, which I'd like you to write, is here. We're given that the mean level in the sample is 9.5, so you'd get 9.5, so sort of 9.5, excuse me, plus or minus the Z confidence level, and the Z confidence, or Z critical value is what it's called. For 99% confidence, we know is 2.576 times sigma, which is given as sigma, the standard deviation of the population, 1.2, over the square root of the sample size. So there are the calculations for this confidence interval, and I've done those already, and you get 9.101 to 9.899, and I'm going to round just for simplicity. I'm going to round that to be 9.1 to 9.9. All right, so that is how you find the confidence interval. Now, the follow-up question is about sample size. How many samples should be selected to estimate with 99% confidence the mean dissolved oxygen level in all samples from the Gallatin with 99% confidence? So I guess I have to reiterate that, but here's the key: to within a margin of error of 0.1 parts per million. Now, from our previous example, we knew that the 99% confidence interval is 9.1 to 9.9. All right, that margin of error is this component of the formula, and basically it's what we add and subtract to the sample mean. Remember, the sample mean was 9.5 from the previous problem, so we're going 9.5 plus 0.4 and 9.5 minus 0.4 to get these upper and lower limits. In other words, in our prior example, the margin of error, or just E is what most people abbreviate it, was 0.4. What this problem is saying, I'd like to be a little more accurate. I'd like to be a little bit more accurate for this confidence interval. So how big a sample do I need in order to not be within a margin of error of 0.4, but to be within a margin of error of 0.1? So this section right here is your margin of error. So E equals the Z critical value times sigma over the square root of n. And to get this sample size formula, which we're going to see in a minute, all you have to do is solve that for n. So solve for n. N being the sample size. Okay, so to do that, the first thing I'm going to do is I'm going to divide, a little bit of algebra. I'm going to divide both sides by the Z critical value. So that says that the margin of error over the Z critical value equals sigma over the square root of n. Now I'm going to do a little algebra trick. If you have fractions on each side, you can actually invert them. So that implies that what you have is that the Z critical value over E, flip the left side, equals the square root of n over sigma, flip the right side. Now remember, I'm trying to find n, so what I'd like to do is isolate that. I'm going to multiply both sides of this equation by sigma. So you get that the Z critical value times sigma over E, the margin of error, equals the square root of n. And the margin of error would have to be given to you in this problem. In all problems, it would be given to you. Lastly, remember, I don't want the square root of n, I want n. So what I'm going to do is I'm going to square both sides. And that gives me my margin of essentially my sample size formula for the population mean. And that is that n equals the Z critical value times sigma over the margin of error, which is given, and square that. All right, so let's go back to the problem. That's how you get the formula. I would like you to know not just that they have a formula, but where it comes from. And here is the same problem with the formula written. And anytime you're asked to do a problem like this, I'd like you to write the formula first from the formula sheet. What formula are you using? Tell me which one you're using. Now, we know a lot of this information. We know that the sample size is what we're looking for, equals, and that's n, equals the Z critical value. Critical value for 99% we know is 2.576 times the standard deviation of the population, which we said was 1.2, over the margin of error, which we want to be 0.1, so a little bit more accurate, square that. So when you put that in your calculator, which I'm going to do right now, I'm going to take 2.576, 2.576 times 1.2, and then I'm going to divide that by 0.1. That gives me 30.912. But I've got to square that. So when I square that, I get a fairly large number, 955.55. Okay, now we're almost done. That's how many samples you need. But how do you collect 0.55 of a sample? In general, you don't. What you do is you say, well, I call it the old school bus problem, that if you have 62 children and each school bus holds 20 children, how many school buses do you need? Well, if you did the division, you'd get 62 divided by 20, and that is 3.1. So 62 divided by 20, the capacity of each school bus is 3.1. So you need 3.1 school buses, but you can't get 0.1 of a school bus, so you round up. It's the same issue here. If you have 0.55 of a sample, you can't get 0.55 of a sample, so what you do for sample size questions is you always round up. So the sample size that we need to estimate the dissolved oxygen level with 99% confidence within a margin of error of 0.1 parts per million is going to be 956 samples. So a fair number of samples in order to get this level of accuracy for dissolved oxygen.